Hello, so this is problem 2294, partition array such that maximum difference is k. So the problem is we are given two inputs. First is the nums, which is an array of numbers, integers, and we also got the second input, integer k. And then the ask is, what is return the minimum number of subsequences that is needed such that the difference between maximum and minimum values in each of the subsequent is at most k. So for example, we have these nums 3, 6, 1, 2, 5 and k is 2. So the solution is 2 because we can partition this into two subsequents, which is 3, 1, 2 and 6, 5. 3, 1, 2 and 6, 5. 3, 1, 2, the max minus the min is 1 minus 3, which is 2. And 2 is less than equal to k equal to 2. So that's why this partition is valid. 6, 5 is 6 minus 5, which is 1, which is less than 2. This is why 6, 5 is also valid. And these two are a valid subsequence because 3, 1, 2 is in the order. Notice that in this definition, a subsequence is a sequence that can be derived from another sequence, which is, for this case, the other sequence is nums, and this is the subsequence, and one of the subsequence, by deleting some or no elements without changing the order of the remaining elements. See that 3, 1, 2 stays in the same order. Okay, so that's what a subsequence is. Then the other part is, another example is 1, 2, 3, where we can separate it into 1, 2, and 3, or another solution is 1, 2, and 3. Look at that the order of the subsequences are the same. Now, that's basically the problem. Make a subsequence with the requirement that the max minus min of each subsequence should be less than equal to k. Once we know the problem, let's think about the tactics. The key point in the tactics to solve this is actually to understand what we can simplify from all these constraints. Look at the constraints of the order. Does it really matter? Remember that we just need to return the minimum number of subsequences. And the key of all these subsequences to be correct is that if the min and max are actually equal to k. The truth is, we don't need to return the subsequences. So keeping this in order or not doesn't really matter actually. Why it doesn't really matter? Let's put it into examples here. Okay, let's go here. Nums 3, 6, 1, 2, 5. And the solution was 3, 1, 2, and 6, 5. In this case, what we really care is actually about the mix and max for everything, right? So in this case, we got 3, 1, 2 by eliminating 6 and 5, and that's it. And the requirement is the mix and max. But does the order of 3, 1, 2 really matter? It doesn't. What really matters for each subsequence, in order for us to know what is the minimum of subsequences that fulfills the criteria that the max minus min is less than equal to k, we need only the min and max. We don't care actually about the order. The order is just a red herring here. That's just what makes you complicate yourself. This is a proof that one of the example where we can actually still get the same answer without keeping the subsequence in order. That's it. When we got this, we know that it is also 2. And we know that 3 minus 1 and 6 minus 5 is the key points to satisfy that it is the right requirement. But does it mean that ignoring the order, we can still keep on getting in the solution? Yes. Because why? Subsequence is coming off from eliminating some of the numbers, right? So it doesn't mean that we have to take everything in sequence. We always can jump certain numbers by ignoring them, which is why we can get this 3, 1, 2 when we ignore 6 and when we ignore 5. So that's the key point here to get into fastest solution for this problem. Ignore the problem of the requirement of the order. Take that out from how to solve this, because regardless it's the same, because we are not asked to return the subsequences. We are asked to return the minimum number of subsequences, where it means we can ignore out the requirement for the order. If we Once we understood that we can ignore out the requirement of the order, this becomes much easier, because what it means is we can sort the nums. We can sort the nums first, and after that everything becomes just a big O(n). What it means is we just scan through it. So we'll start the subsequences with something like this. Okay, so once we got these subsequences, or we can have it, imagine it like this. So we have the first subsequences which consists of nothing, and then what we do is we just need to go through here from left to right, and whenever this is empty, what we do is we're going to initialize it. That become the min. Why it's the min? Because we sorted it already. We started by sorting it. So we know that the very first it fills in that empty array, it will be the first number, the minimum numbers for that subsequence. Once we got that, we just scan through it, and then we always do the minus. So when we reach the second index, which is the index number 1, what we do is we do this 2 minus the min. The min was 1, right? And the min was 1. It means we compare it then with the requirement that it should be less than equal to 2 to make it keep on the same subsequence, and it is. And so what happened is we move on. We don't do anything. We don't need to store it here, because what we really care is just the min and max. We just need to loop, explore through, and whenever it's still within the constraint, we go on without creating a new subsequence. So the next one will be the 3. Now we are looking at the 3, we do the same thing. 3 minus 1, which is still satisfying, less than equal to k, which is 2, because 3 minus 1 is 2. So we don't do anything, we move on. Now we move on to number 5. When we do 5 minus 1, it becomes 4. This violates the condition that 4 must be less than equal to k, because k is just a 2. So when this happens, what we really need to do is we will initialize another entry in the subsequence, because at that point it violates, it means it will belong to a new subsequence. So 5 will be in the new subsequence and become the minimum value for that subsequence. Once we got this, we move on. Now it will be the number 6. Now 6 will be minus 5, because this is the latest subsequence we have. And this will be 1, and 1 is less than equal to k. So 6 belong to here. After that, that's it. That's the end of it. And once it's the end of it, we just need to return the length of s here. And that will be our answer, which is in this case is 2. So ln s is 2, and this will be the minimum number of partition that satisfies the requirement. Okay, So let me summarize the tactic here. The tactic is basically we ignore the order. And then after ignoring the order, we make it simpler by sorting the nums. After we sort the nums, we just going through it one by one with the conditions of if there is nothing of it, we make it the minimum, then we check in until we find that it is not the same with k anymore. It means a new additional subsequence. After all is explored in the nums, we just return the length of the subsequence, and that will be the minimum value already. Okay, so that's a tactic. Now let's go to the code implementation, which I've already written it. Okay, so we just do what we say in the tactic. First of all, we sort it out. We know we can sort it out because the problem is only asking us about the number of sequences, not the subsequences itself. So we can ignore the order. After we sort it, we initialize the subsequences, which is this actually with the empty first one is empty, and then after that we also keep on the index. So this is pointing to index to the subsequence paths here, which is starting of course with index 0. After that we just explore the numbers in nums one by one, and this is when the subsequent si is still empty. When it is empty, we just append it directly, and it means it's the minimum. Okay, it's the minimum value for that subsequence. Otherwise, we need to do the check of the conditions, whether the new potential max, which is the new n that we are looking at, minus the known min for that subsequence is still fulfilling the k constraint. If it is, then continue. We don't need to do anything. Otherwise, we will append a new subsequence, because once it violates, it means it requires a new subsequence, and that n also will be the minimum value for that new subsequence. That's why we do this. And once we do that, of course, we need to increase the index that is currently pointing to the subsequence paths, and so on and so forth until all the end. We just need to return the length of it as the answer. When we submit this, that's it. It's accepted. Okay. So that's about the code implementation in Python. And how about finally the time complexity? The time complexity in sorting here will be big O and log n. That's a basic knowledge about that. The fastest in sorting is n log n, and the one implemented in Python by default, of course, the fastest in terms of the big O. And then this one is just an initialization. This is a for loop of big O n. And of course is the length of nums here. And then this is just comparison, appending. This is just comparison, appending, comparison. So everything inside here is just a big O1. Therefore, the for loop here stays just a big O(n). And then returning the learn, of course, just big O1. Now, all the sequences, of course, in big O is an addition. What it means is take the worst one. The worst one here is actually just the sorting. So the time complexity is big O and log n. That's it for this problem. This is a medium level problem. Thank you all for listening in. Bye.